Welcome to this video on domain and range of a square root function. A square root function is represented by a function with the square root symbol. So what you need to remind yourself of is that whatever goes under that symbol, square root symbol, has to be greater or equal to 0. So this is immediately a red flag, the signal about your possible domain. So since x is greater or equal to 0, there is no way that you can grab a negative number, plug in, and find a solution to it. So immediately after you recognize these restrictions, the domain will be denoted as x is element of R such that x is greater or equal to 0. So that's a domain for this square root function. So if this is the case, so any possible value of y must be at least 0, then you can anticipate some positive numbers. And then the greater the number of x is, the greater the number of y should be. So this is a curve that should represent more or less a possible graph of a square root function. So what is the range for this type of function? So from this graph, from this example, you can see that the range will be a set of real values that are greater or equal. So we can simply put that in writing as R, representing a range. So y is element of R such that y is greater or equal to 0. So this is identical restrictions as for the domain. So x is greater or equal to 0, so is y. So this is the fundamental change that we see now working with a square root function. Just to recall, any type of polynomial functions, no restrictions for the domain at all. There were restrictions related to the range, but domain was an entire set of x-axes. With a square root function, this changes. Now, let's move to the next example, square root 2x plus 1. So if you recall this fundamental rule about finding a square root of any number, whatever goes under the symbol or inside of a square root must remain at least 0. So 2x plus 1 has to be greater or equal to 0. So solving this inequality, further you will say 2x is greater, so plus 1. 2x is greater than negative 1, which means that x is greater or equal to negative 1 over 2. So now, any number starting from negative 1 over 2 will work. So if I were to mark its location on that x-axis, negative 1 over 2, so I expect my graph to be shown to the right, because I have to be greater or equal to negative half. So my square root function more or less should look somehow like this. So what do you think the range will be? The range of this, for this example, will be very much the same as the first equation. It will be all set of real values such that y is greater or equal to 0. To summarize this, the domain is a set of real numbers. X is element of R such that x is greater or equal to negative 1 over 2. Close the brackets. Okay. The range will be a set of real values of y with the following restrictions: that y values are greater or equal to 0. Okay, moving down to example number 3 right here. Well, I was going to highlight it, not mess up with this beautiful equation here. So let me select the highlighter one more time. Okay, now, so as you can tell from this formula here, we have variable x squared, and then 1 is added to it inside of the square root. So when you square a number for any type of input, the output is positive. So negative 2, for example, squared will give you 4 plus 1, 5. Positive 2 squared will be 4 plus 1, also will give you 5. So what you can see here, all of a sudden my square root function has no restrictions for its domain. So sometimes this is possible. You would most likely attempt solving this inequality. Let x squared plus 1 greater or equal to 0. Plus 1, I said. And then x squared will be greater or equal to negative 1. And this is a true statement. X squared plus 1 is always greater than 0. It's never equal to 0. So no restrictions for the domain. Immediately you would say that domain is a set of all real numbers. So it's a common sense. Now, the range, the lowest value of x will be here 0. Why 0? So why do we say that the lowest value of x that will interest us it will be 0? Since you're squaring an x number, so anything other than 0 squared will be positive. So this is why the lowest value of x that we can consider in this example will be 0. 0 squared is 0 plus 1 is 1. So the lowest value of y will be when x is equal to 0. And then gradually you will start increasing on the right-hand side. And since the domain does exist for all real numbers, you will increase on the left side as well. So by inspection you can predict several points of the graph to the right, to the left, and you will agree with us that this is a possible graph for this type of square root function. So the range now is defined as y's element of R such that y is greater or equal to 1. So this is very similar to a quadratic function or polynomial type of function where there is a local minimum. There is a lowest value, and anything greater or equal to that is part of the range. To summarize, now, with almost any type of a square root function, there is a restriction. So what you have to do always, most of the time, you set the value, the expression that goes inside as greater or equal to 0. And you solve it. Once you solve it, you will know this is what will be the set of x values that satisfies this condition. So solving that inequality, so any expression is greater or equal to 0. Any expression that goes under the square root symbol. You find a solution to that expression, and based on the solution you formulate the domain. The range usually is starting from 0 going up. Unless there is a negative sign in front, then that will change to the opposite. But sometimes there are no restrictions at all. So this is illustrated by this last example right here. So no matter what x value is used, produces always positive number under the square root symbol. Therefore, there are no restrictions. So this is something that you have to be aware of. Do not just jump into conclusions saying all square root type of functions have a limitation on its domain. So be careful before you make that conclusion. So this is it for that video. Thank you for watching it, and I see you next time.